Good afternoon. Thank you for coming. My name is Gabriel, and I'm also part of the same group designing and implementing the radiation dosimeter for the consumer market. Specifically for my thesis, I worked on the actual calibration experiment. So just a quick overview, I'll go over the problem statement and the engineering design process which I followed. Then a quick literature review, and then the actual designing and conduction of the experiment. Coming up with that calibration factor itself, implementing it to our dosimeter, and finally some conclusions and recommendations. So the purpose of my thesis was to conduct and design that calibration experiment for the purpose of coming up with the calibration factor. As a secondary purpose, I also used IEC guidelines for dosimeters to measure different parameters such as energy dependence, linearity, and response time to the dosimeter. And on top of this, I wanted to do so safely. This is how the group kind of comes together. So ideally, I would be using the final product form from Mali to conduct the calibration experiment, and then use the MCP results from Derwin to calculate the calibration factor, and finally implement it on the software side of the dosimeter. So as Ali mentioned, during semester one, we followed the first couple stages of the design process. This semester, I really focused on the analysis, which is actually coming up with that calibration factor, and then the implementation by implementing it on the software side. And of course, refinement is happening throughout this process all the time. As per literature review, I was following an IAEA guideline for calibrating radiation dosimeters. Basically, you want to calibrate because you want to ensure that the instrument is actually functioning as it is intended to be. You want to be able to test it in a controlled environment, test the response of it to different, for example, energies, angles, etc. And finally, you want to optimize the actual accuracy. So by coming up with these calibration factors, we're able to optimize overall the accuracy of the dosimeter. So just some nomenclature. The response is the indication, so what exactly the dosimeter is indicating, divided by the measurand, or the true value. And for this purpose, it was going to be the MCP model. And then the calibration factor is the reciprocal. But because we did this with different energies and at different angles, I would take the average response to calculate the calibration factor. So here's the experimental design in an algorithm format. So essentially, I'm using 3 different sources as recommended by the IAEA, measuring different dose rates at different angles, and then repeating this so I can actually take an average. And then for each iteration, I would take a background reading and then take the measurements at 10 seconds, 60 seconds, and 120 seconds to help see how the detector responds over time. Of course, there's limitations that I had to abide by. So first of all, we didn't actually get that product form done in time because of the issues with the USB. So as Ali said, instead we used LabVIEW virtual instrument connected to the DAC to actually obtain the data. Because these source activities were so low, we had to get to distances that were very close to the detector. And for the purpose of modeling it in MCNP, we were actually so close that we couldn't change the angle because we'd end up inside of the phantom. So for that reason, at 1 microsievert an hour, we could only test at 0 degrees. But for 0.1, we could test that at the full range. The background measurement had to be up to 5 minutes. This is basically just a intrinsic property of the dosimeter. For background readings, it gets about 0.3 counts per minute. So if you multiply that out, you need roughly about 4 minutes to actually see a count. And then if I were to actually conduct that entire experiment that I showed in the last slide, it would take roughly 100 hours, which isn't very obtainable. So after reducing the dose rates and the angles, and then accounting for this 5-minute background time, I actually reduced the repeated measurements to just 3. And finally, as Derwin mentioned, there was an error when calculating the distance from the source to the detector. So we had to use microshield as our measuring values. So this table shows the different configurations that I completed through the experiment and Derwin modeled in MCNP. So the first 3 are designed to give you a dose rate of 1 microsievert an hour. And again, I'm only doing them at 0 degrees. And then the latter 3 at 0.1, which I could do at a different angle. So as you can see, the distances are really close, which is also an issue for human error. So instead of 3.7, if I was at 4.2 centimeters, it's going to have a pretty good difference in terms of what the dose rate that we actually want. So here's the experimental setup. So starting with the source, I had it taped to a ruler that was attached to a camera stand to move it off the ground. And same thing with the detector, I had it taped to a ruler that was away from the table. And this was basically to get away from scattering areas and to make the model as similar as possible to MCNP, which was just free in air. And then from the detector, we connected the output to the NI DAC, which is then connected to USB to my computer to get the data. And then the actual circuitry is powered by USB to the phone as the final product form intended. So then my LabVIEW program gave me the counts at 10 seconds, 60 seconds, and 120 seconds. And here's everything all together. So you can see that the source is about 70 centimeters off the ground and the detector 20 centimeters from the table. In terms of safety, all three of us underwent radiation training protection here at the university. We had a permit for the lab so that we could store the sources there. So we had to mark the lab as a radiation zone. The sources were always stored in a locked cabinet, which only I have a key to, and the RSO at the school. They're stored in this lead tank. And this was basically done for ALARA. It was a requirement actually to bring the dose rate down to 2.5 microsievert per hour. So this is if you are storing sources in a lab or a medical setting, this is what we have to abide by. Minimizing exposure time is basically anytime I had to move around the experiment configuration, I put the sources back in the shield, put it away, do what I need to do, and then get the sources back out. And in terms of distance, I was far away from the sources. You saw that even at 11 centimeters, 0.1 microsievert an hour, put a couple meters almost background. In terms of personal protective equipment, I would bring gloves when handling the sources, and then obviously I would wash my hands afterwards. And I also practiced beforehand. So this last picture here shows me practicing with a tuning. So basically having the gloves on, practicing taking the sources out of the plastic bag and putting it where it needs to be. And this also helped me reduce the experimental time and thus my exposure. And finally, in terms of emergency preparedness, I knew who to call if something were to go wrong. So this graph at the bottom shows the response, which again is what we measured over what we should have measured. Not as clean as Derwin's. And this is basically because the measurement time should have been longer than 2 minutes. So what was happening is that we were actually getting measurements that were below the minimum detection limit, which was calculated to be 0.79 counts per minute. So that removed a lot of the data, and then so this is basically a result of poor statistics. So what I was able to do is average this over energy and angle to come up with a calibration factor. And it could actually be done at a different dose rate because we could analyze the counts that were coming into the detector and then have a rough idea of what dose range we would be in. And then we could actually apply a specific calibration factor to that dose rate. But as you can see, they were very similar. I also tried doing an energy-weighted calibration factor, which was recommended by faculty. And you'll see that both of them actually reduced the percent error quite significantly, but just the regular average performed better if we averaged between the two of them. But as you can see, I was able to reduce it almost 100% after calibration. This energy dependency graph basically shows how the detector response changes as a function of the energy from the source, even when you're supposed to be at the same dose rate. So you can see over here we have 1 microsievert per hour, but at different energies, according to the source, there was actually a different response. So these dashed lines actually represent the IEC requirement. And after calibration, which are these two colors, you can see that it actually falls within that, but only at 1 microsievert an hour. So at the lower dose rate, it didn't. But again, that was because the measurement time would have to be increased, so we'd be at better statistics. So finally, now that we have this calibration factor, we were able to implement it on the Android application. So we decided to just make it built in, so it was hard-coded. But this could also have been done dynamically, where the user has the ability to change the calibration factor for different scenarios, or perhaps through an application programming interface where the developer knows best what sort of calibration would be required. So you can see that the detector itself, through Ali's interface, will get the counts per minute, and then we can convert to dose that includes that calibration factor. So in conclusion, I was able to design and conduct a fairly successful calibration experiment for the purpose of coming up with that calibration factor. As a group, we were able to interface the dosimeter to a smartphone via USB and then collect that data with an Android application that included the calibration. Finally, we showed the final product form in the NX drawing that could potentially be printed, 3D printed. Recommendations for future work would be to perhaps look into standards for non-commercial radiation dosimeters, because that's what the IEC requirements are for. So after Fukushima, you see this huge spike in these low-cost dosimeters, but there's really no standard for them. On top of maybe increasing the activity so that we can get better distances and to increase the measuring time to get better statistics. We could also look at recreating the counts to dose conversion, which was provided by the manufacturer, and doing so at various energies. So thank you very much. Questions? Yes.
So you said there was errors in your experimental results, so you had to redo it in microshield?
The error was in the calculation. So I was calculating the distance for each source to obtain the dose rate. So the error was in that calculation. So the experimental results are exactly what they should have been, and the MC&Q results are exactly what they should have been. But there's an error aligning them. So we used microshield to realign them, and we used that for the calibration factor, not the MC&P model that differed by that factor too. Mara?
What is the biggest challenge that you faced in the entire project?
Oh, that's a great question. I'm going to bring it over to the USB because we clearly didn't anticipate how difficult that would have been. And if we finished it on time, we would have had something that was just attached to your phone, and we could have actually ran the experiments with that. So that was the most challenging part. Yes?
I was wondering, where would the dynamic calibration factor be useful? Like an example.
Absolutely. So perhaps if for whatever reason you understand the sort of field that you're going to be in, and so you have more information on maybe the energy and the dose rate, you might be able to optimize that calibration factor, because I was just taking it over every energy, which is essentially like a best case scenario if you were to just walk outside and there's some sort of sources and go and measure. But if you had more information about the application that was being used in, perhaps you could optimize that calibration factor.
Because I was just wondering, this is for consumers, right? For like people, for the general public. Yeah. So I was just wondering, having a dynamic calibration factor might not help.
Yeah, but of course, sometimes you hear concerns like, oh, on the West Coast we have all this cesium. Well, okay, we know the energy is cesium. Perhaps we know something about the activity. So maybe in that scenario, we could maybe optimize the calibration factor. Thank you.
How would your final product pass this compared to existing personal dosimeters?
How would it compare?
Yeah.
So we presented a number of different product forms. So for example, we hypothesized having something that was like a smoke alarm that you keep in your house. The other thing is, I think we could leverage information technology. Like Ali was saying, we could come up with different applications that would, really create a community and really leverage that, and really leverage the availability of information. So this is something that the companies aren't thinking about right now. They're just sending out this dosimeter and you have it and you're done. But there's actually a lot you can do by aggregating this information and putting it in different content. I think that's where the competitive advantage is. That's where the business case is.
Can I just follow up on those last two questions?
Yeah.
You being the business guy. So okay, on that, if we in this room collected, I don't know, $50,000, and we said we really think this is cool, and we want a business to help develop a business from this, what do you think is the best prospects, and where do you see the biggest pitfalls to develop something like that from this?
So in terms of pitfall, we're using a dosimeter that we just picked up and made some adjustments to the circuitry and had it work for our scenario. So we'd probably have to go down fundamentally, because we can't patent this for that exact reason. So fundamentally, we would have to build that detection process. Sorry, what was the other part of your question?
If you think there's a market for it.
Market. Unfortunately, the market will probably be where there's nuclear disasters, because that's where people are really concerned. But I mean, even like locations where people are near nuclear power plants, so I think Ontario would be a good market. Obviously, the Japanese market is huge, and there's actually been tens of products just within that 6-month span that Fukushima happened, where companies were just talking about these products. So there's clearly a market over there, but it might be a little saturated. But in terms of Ontario, there isn't really a product here, unless you're going to purchase something that was built there.